Here you can see the note on van der Waals forces. In other words, instantaneous dipole, induced dipoles. You can see ID forces. The things we have discussed about so far, first point. These van der Waals forces are the weakest intermolecular attractive forces. They are the only possible attractive forces between non-polar molecules. Oh, we are talking about non-polar molecules. Example, what are the examples for non-polar molecules? Noble gases, there are no charged particles. Halogens at room temperature, example, F2, Cl2, Br2, I2. And also oxygen, hydrogen, S8, P4. They are not ACT, ETC, etc., etc. Some examples are there: CH4, CCl4, CBr4. Here, the boiling temperature is given. CH4 boils at negative 164. CCl4 boils at 77 degrees Celsius. CBr4 melts at 89. Why they melt and boil at low temperatures? Because their van der Waals forces are very weak. This is about formation of intermolecular attractive forces, van der Waals forces. Formation of instantaneous dipole, induced dipole attractions. This is what I explained earlier. We'll complete this table now. First one. Electron cloud in non-polar molecules constantly move in a random manner. Electrons move. When electron cloud concentrate towards one side of molecule, a temporary dipole is formed. A temporary dipole is formed in the molecule. That means slight positive and slight negative charge on either side of the molecule. This is called self-polarization. Okay. We can take this whole thing, probably I'll take these three molecules and paste in the next one. Okay. And then in the second diagram, in the first one also we can show, oh no, we'll do it on the second one. The first diagram shows the particles coming closer. In the second one, you can see here, see electron concentration decreases here. And here also. And on the other side, electron concentration increases. This side is delta negative, positive. Right-hand side is delta negative. Middle one has changed. Accordingly, the right-hand side one also changes. Not that, the left-hand side. Earlier molecules were not charged. Now the molecules are showing some slight charge density. and we had to show the van der Waals force formation. Okay. Those are the ID forces. Please copy down the diagram, please. Now let's talk about the strength of hydrogen bonds, not hydrogen bonds, van der Waals forces. The strength of these forces depends on two factors. The number of electrons in a particle, I explained this earlier also. Surface area of particles to interact with the neighboring particles. When the surface area increases, the number of contact points increases. Contact points are the areas in a molecule that can interact with other molecules. Van der Waals forces are relatively strong in molecules where there are more electrons and show larger surface, larger size. Explain how van der Waals forces are. I'll take this separately for a discussion. Explain how van der Waals forces are formed by non-polar molecules. It's a partial question. I want to discuss this to teach you how to get 3 marks. Explain how van der Waals forces are formed by non-polar molecules. See how we get the 3 marks. When electrons in non-polar molecules. When electrons in non-polar molecules move at random, they get concentrated in one area. They get concentrated in one area. When electrons in non-polar molecules move at random, they get concentrated in one area in a process called self-polarization. You get 1 mark for this point. Because of electron movement, they get self-polarized. 1 mark. Afterwards, the self-polarized molecules force the neighboring molecules to undergo polarization. This is called induction of polarity. Induction of polarity. So this is 1 mark. And the next one, the oppositely charged the oppositely charged ends of neighboring molecules the oppositely charged ends of neighboring molecules or particles attract each other through weak electrostatic attractions. You get 1 mark for this. See, there are 3 marks. This question was taken from a past paper. How van der Waals forces are formed. We go to the next one. Next question. The following diagram shows how enthalpy of vaporization changes for noble gases. What's the meaning of enthalpy of vaporization? I had to explain this to you first. The following graph shows how enthalpy of vaporization changes for noble gases. Children, see, enthalpy of vaporization means the energy change involved to evaporate a substance. When you want to evaporate a substance, intermolecular attractive forces should be broken down. So vaporization is all about breaking intermolecular attractive forces. See, noble gases: hydrogen, helium, not hydrogen, helium, neon, argon, krypton, and xenon. When you move down the group 7, you can see this is small particle size. This is helium. And this is neon. And if you write argon, argon is a bigger molecule or bigger particle. And krypton. What happens when you move down? The size increases. At the same time, the number of electrons present in molecules also increases. So what happens? Van der Waals forces increase. So more and more energy is needed to break them, and the enthalpy of vaporization increases. That is, more and more heat energy is needed to evaporate them. That simply is the work. You know the answer. Right, like this. ID, ID,